Final Lagrange multiplier example. We have an example where we're trying to find the shortest distance or the point on a given plane that's closest to a given point. This is our given point, -2, 5, 1. This is the plane, 2x plus 3y plus 6c equals 10. So that's our constraint. We want points that lie on that plane, and we want to minimize a distance. Whenever we want to minimize a distance, we use the distance formula, but we use it squared. We minimize the square of the distance instead, because the place where the minimum occurs will be the same either way, and it's way easier not to deal with the square root. So we minimize the square of the distance. Notice that we have three variables, unlike our previous two examples where we had just x and y. Now we have a z involved, but the idea is the same. Lagrange multiplier equations are the same. The process is the same. So let's get at it. We have grad f must be lambda times grad g. So grad f in this case is 2 times x plus 2, comma 2 times y minus 5, comma 2 times z minus 1. That's the gradient of f, and the gradient of g is just 2, 3, 6, so that's really nice, at least. And we put this together, and our equations look like the x component, we have 2x plus 4 is going to be lambda times 2. For the y component, we have 2y minus 10 is lambda times 3. And for the z component, we have 2z minus 2 is lambda times 6. And then our last equation, as always, is the constraint curve. So 2x plus 3y plus 6z equals 10. I said constraint curve, but now in three variables, it's a constraint surface. That's our system. 4 equations, 4 unknowns, and we need to find the x, y, z. That'll be the point where we have a minimum distance. So in this case, I'm going to start by just taking the first equation and solving for lambda. So lambda is x plus 2. I'm going to take that, I'm going to plug that value into the second equation. The second equation becomes 2y minus 10 equals 3x plus 6. If I plug that value of lambda into the second equation, if I plug this value of lambda equals x plus 2 into the third equation becomes 2z minus 2 equals 6x plus 12. And these two equations here, if I solve for y and for z, I get y equals 3 halves x plus 8, and I get z equals 3x plus 7. So that's y in terms of x and z in terms of x. So if I have both y and z in terms of x, I can plug those values into the constraint curve, into the fourth equation here, and I get 2x plus 3 times y. Y is 3 halves x plus 8, plus 6 times z. Z is 3x plus 7 equals 10. And this is all in terms of x now. So it's all in terms of x. That means I can do the work and figure out what x is. This is 2x plus 9 halves x plus 24 plus 18x plus 42 equals 10. Let's see, 9 halves plus 4 halves is 13 halves plus 36 halves is 49 halves. So 49 halves times x equals, let's see, 42 and 26 is 6. 42 and 24 is 66. 10 minus that is negative 56. And so we have x equals negative 112 over 49, which reduces to minus 16 sevenths. So that's x. There's one solution for it. We happen to know what y and z are in terms of x. Right? We have y and z in terms of x here, so we just plug in our value for x, and we get y is 3 halves times negative 16 sevenths plus 8, which turns out to be 32 sevenths. And z was 3 times x, which is negative 16 sevenths, plus 7, which turns out to be 1/7. And so we have a solution. We have a point, negative 16 sevenths, comma 32 sevenths, comma 1 seventh, and that is the only place where we can have a max or a min of our objective function, the distance, subject to our constraint, subject to the points being restricted to the plane. Since that's the only possible max or min, and we know there has to be a min, this is it. So that is the minimum distance point, the point that leads to the minimum distance. That's the point closest to, what was our point? Negative 2, comma 5, comma 1. Negative 2, comma 5, comma 1. That's the point on the plane that's closest to that given point, negative 2, comma 5, comma 1. We got there through Lagrange multipliers, and in this case there were 3 variables. So that's a thing that can happen. And as you saw, we deal with it in the same way. We use the Lagrange multiplier equations and we solve for x, y, z.